Hello everyone. Today I'm gonna be presenting about the applications of data mining breast cancer imaging. So first we're gonna go through the introduction, the methods, the results, and then the conclusion. For the introduction, what is breast cancer? Breast cancer is the abnormal cell growth in the breast, and we have two different types of cells. They have malignant cells and benign cells. The malignant cells are irregular in shape and very sharp, while the benign cells are smooth and round. According to the American Cancer Society, 2,700 men are diagnosed with breast cancer, while 530 men died, and 287,000 women are diagnosed with breast cancer, while 43,250 women died each year. So the breast cancer diagnostic tools that we have so far are MRI, mammogram, biopsy, and ultrasounds. We have other more, but in this case, we're just gonna be talking about ultrasound imaging. So for the advantages of the ultrasound, we have that it provides the image of the tumor. It is low radiation and is relatively cheaper than the other options, which were the MRI, mammogram, and biopsy. For the disadvantages is that sometimes it's hard for the naked eye to classify breast cancer as benign or malignant due to the low quality images. Therefore, we need help of machine learning to overcome this problem. However, due to the ultrasound fuzzy nature, it's very hard to design a segmentation and diagnosis method. Computer-aided diagnosis help physicians specifying treatments and surgical plans. However, it's very hard to design a CAD system for ultrasound images because of the low quality of the ultrasound, and also the tumors can vary in size, shape, and have irregular ambiguous boundaries. However, computer-aided diagnosis have improved during the years with machine learning and deep neural networks, and they have boosted its capabilities. However, it is still open for improvement. So for this research, to improve breast cancer classification, a convolutional deep encoder model can be implemented for breast cancer segmentations and feature extraction to later be used for classification. Now we're going to discuss about the methods. So the data was for the data collection, it was collected in Bahia Hospital in 2018. It was collected from women ages 25 to 75 years old. In total, there were 780 ultrasound images, 437 being benign, 210 malignant, and 133 normal. So the models that we're going to discuss in this paper, in this presentation, will be an 8-net model, which was used for feature extraction and segmentation. PCA, principal component for the PCA, we're going to use for dimensional reduction. And then finally, we're going to use a random forest for classification. So first, the outer encoder model that we use for this research was an 8-net, which is a backbone network for multitask learning. In the encoding part, we use convolutional layers to compress the image, and a deep neural network structure was used in this case, which lowered the bits to 4 biomarkers. To 4-bit biomarkers, and spectral embedding methods and Laplacian eigenmaps were used to reduce 354 radiomics features to only 4. The decoding part or the compression part of the signals is used in the convolutional layers to decompress and give the output, which is the segmented tumor for the ultrasound image. On the other hand, we have the horizontal connections, which were used for feature extraction. In this case, 4 features were extracted. Now in the autoencoder model, the inputs were the ultrasound images as we discussed before. So we give the model the normal images, malignant images, and benign images. And then the outputs were the segmentations of the images and the 4 features that we talked about that were extracted in the convolutional gradients. 635 cases were used for training and 155 cases were used for testing. In addition, we also extracted more features with Radiomics library. So we extracted the traditional features from the original data, and then we reduced it with PCA from 354 to 5 features. So for the PCA part, we reduced the traditional features to 5 components, and this is the representation of components 1 through 3. As we can see, some components are different from each other, which is what we want for the PCA, since 5 components represents the whole data, and the 5 of them are supposed to be really different from each other in order to represent the entire data. So in this case, some of them are different but some components are alike to each other. Here, components 3 through 5, we also have the same. We also got the same. Some components were different, but some components were really similar to each other, which is really not what we're looking for in this case for the PCA, for the principal component analysis. So an example of this will be component 3 and 2. We can see that these 2 components are very different from each other since we perform a linear regression between the 2 of them, and the lines are kind of like not touching each other, which means that we want this since the two data since these 2 components are not going to be similar from each other. However, for components 3 and 2, we see that the linear regressions are touching each other, and we don't really want this, and this is a really bad representation for the data, and this can later have a really bad impact for the classification model since the data is not being fully represented with these 5 components. So this is really the downside of the PCA. In this case, it's not really 100% accurate. So after we got the data from after we reduced the traditional features to 5 features with the PCA, and after we got the 4 features from the 8net, we're gonna combine these 2 features to later give it to the classification method, and we do this in order to make the method more robust, which is gonna be the random forest method. After that, the inputs for the random forest, as we said, will be the features, which consists of the 4 ANET features and the 5 PCA features. Later, after that, the random forest performs binary classification, and the benign features will be given as 0, and the malignant features will be given as 1. Now we're gonna discuss about the results. So for the breast cancer segmentations, we can see here that the model segmented some areas of the breast. However, there is some examples, as we can see for A3, that it was an unsuccessful segmentation, and this just gives us that the model could segment some areas, but there is still room for improvement in the future. Now for the random forest results. So for the random forest results, it tells us that the measure of the ability of the classifier to distinguish between the classes, it's 75%. When we use the hyperparameters, which with estimators 10, depth 3, in a random state of 88. For the conclusion, so we use an ANET in order to compress the images from high dimensionality and extract the features. In this case, we extracted 4 features, and PCA was performed in traditional features in order to reduce dimensionality. From this step, we got 5 features/components. Both ANET and PCA features were combined and then given for classification to random forest algorithm. And in the random forest algorithm, the measurability for the classifier to distinguish between the classes, which are the malignant classes and the benign, and the malignant and benign cells, it's 75%. Despite the number of features extracted from the cases, however, it is necessary to incorporate clinical data to achieve high classification diagnostics. Some of the limitations, as I said before, as I just said, were the absence of clinical data, and the model demonstrates its capabilities of some automatic segmentation, as we said, as we saw on the previous slides. And for the future, it will be better if just one model is built for segmentation and classification instead of having 2 models, which is the ANET and the random forest. Thank you.